Hello, chemists, and welcome back to lesson 2 of our video series on kinetic molecular theory. So, kinetic molecular theory um, is really just a way of explaining the way molecules move. We see that in the words here. We have kinetic molecular theory. So, movement is kinetic, molecular, molecules, and theory is our scientific understanding of it. And basically all that KMT is a series of rules and postulates, they say, about the way molecules actually move in our world. And that helps us explain solids, liquids, and gases like we were looking at yesterday. So solids, just to review, are hard to compress with high densities. Densities is the amount of mass in a given volume, so there's more particles of it in a smaller area. They have a definite shape and definite volume. They're not flowing or anything, and they're not easy to diffuse because they're solid. Liquids are hard to compress and less dense. They have no fixed shape but a definite volume, and they're fairly easy to diffuse. No fixed shape means they'll take the shape of the container, but 50 milliliters of water is 50 milliliters of water, whether or not you have it in a bowl or a cup. Gases are easily compressed with low densities. They have no fixed shape and no fixed volume. They'll just take up the entire container, and they're easy to diffuse. So with gases, you see that if you put them in like a 1 liter bottle, it'll be the same amount as if you put it in a 2 liter bottle. What changes this pressure? We're going to look more at that next week. Anyways, with all that in mind, let's keep going. So kinetic molecular theory is a theory explaining how gas particles behave. If we know how gases behave, we can make predictions about solids and liquids, because remember, it's all the same compound, it's just at different temperatures. Everything will be a gas if you heat it up high enough, and then if you cool it down enough, it'll become solid. So these movements can give us information about solids and liquids as well. The major assumptions or postulates are as follows, and these are really the core of kinetic molecular theory. So I invite you to write these down, or just make sure you make note of these in your booklet or wherever you're taking notes, because these are important. So the major assumptions or postulates, we have 4 of them. Here's some historic scientists. You don't have to actually remember who these people are. I'm not going to test you on that, but it's interesting to see some like fancy names and some famous names. So first, postulate 1 was from this guy named Bernoulli, and he said particles are very small, and most of the volume of a gas is empty space. Particles are very small, and most of the volume of a gas is empty space. This means that when you have, let's say, a bottle of air, let's say you just emptied out a bottle of water, filled it up with air, and closed it, that means most of the volume inside is actually going to be the space between the molecules and not the molecules of gas themselves. Now, this sounds kind of silly, like especially initially, because it's like, no, matter is what takes up space. But with gas, we see that it's spread apart and moving very quickly, and that most of the volume actually is the empty space in which gas can move. You'll see some images of that over the next couple weeks as well. Postulate 2 came from Maxwell, and it says particles constantly move and collide with other particles or the container. So this means if you imagine like gas bouncing around a bottle, it's going to keep hitting the side and hitting the side and hitting the side, and that'll change its direction and speed. Postulate 3 is from Boltzmann, and it says collections result in no change in energy, and the average kinetic energy of a sample depends only on temperature. So what we're going to take away from here is that the temperature is the main thing that changes the motion of particles. So as we heat something up, it's going to start moving faster and have more energy, and that'll lead to state changes we'll ultimately look at. So like if you heat up an ice cube, it'll melt. If you heat up water, it can evaporate, things like that. Postulate 4 is from van der Waals, and he said there are no forces of attraction between particles or the container. So this is just to say that they're not going to be drawn into each other. They're all going to be moving on their own paths randomly. Cool. So take a second and pause here and maybe write down these 4 postulates or make note of them in your booklet. So postulate 1 says particles are very small and most of the volume of gas is empty space. Excuse me. So remember, gases are easily compressed with low densities, and they have no fixed shape and no fixed volume, and they're easy to diffuse. So what we see here is a gas inside a container, and you can see it's bouncing around and moving, but most of the volume is actually just empty space. And this is typical of gases. They're just going to be bouncing around and they can be compressed. You can imagine you could make this container smaller and the gas would still be able to live in there. It would have what we call a higher pressure, but that's more for next week. But just keep that in mind that gases are moving around the entire container and they can be compressed easily because most of the gas volume is empty space. You can compress into that empty space. The actual particles only take up this small room in the corner. Obviously, that's not what we see in actuality. That would be more like a solid arrangement. So gases aren't just going to stay clumped together down in the corner of like a bottle. They're going to spread all out everywhere and leave lots of space between them. So yeah, this is a nice analogy here. We know that gas surrounds us as air, and obviously when we're walking through the air, we're not just butting our heads constantly on gas, even though we are moving it, but we can easily move the gas surrounding us in the atmosphere and walk down a hallway or get up from our chair. We're not just like trapped by all like the solid gas. We have lots of space to move around. Okay, postulate 2 says that particles constantly move and collide with other particles in the container. So gases, the point that we're looking at here is they have no fixed shape and no fixed volume. Gas particles collide with the sides of the container and exert a force, that's gas pressure, which we'll look at more later again. So if you just imagine that this gas molecule is inside this box, it's going to keep moving and keep bouncing just like forever and ever and ever and ever and ever, like a game of ping pong or something. And that's going to happen constantly. So we see that in here when there's like different molecules. They're going to be moving around and they'll randomly hit each other, and they're going to constantly hit the wall and hit other particles, and that'll change the way that they bounce. If you look at these red ones, they get hit by the blue ones and change their course. And that's what we see. Gases are just a series of interactions in which these molecules floating around inside of something are just hitting each other, speeding up, changing directions, and that's how we see gases move. So particles are in constant random motion and are only limited by collisions with the walls of the container. With all these slides, feel free to just like play them back and take another look because they're good visuals and I recommend internalizing them. So Maxwell and Boltzmann. An object in motion has kinetic energy. That's a buzzword that you may have heard from physics or in grade 10 when we were talking about grade 10 science when we were doing motion. Kinetic energy is the energy that something gets when it's moving. Kinetic means movement. Energy obviously means energy. So kinetic energy is directly related to the particle speed. If something's faster, it has more energy. So of any amount of particles, there's going to be a distribution of kinetic energy where some of them will be lower energy and some of them will be higher energy. This is at a given temperature, but we have like an average kinetic energy. Not all particles have the same energy level at the same temperature. Some have high energy, some have low, but most have this average amount. This is just like a distribution, we call it, like an average or a bell curve or whatever. But we're saying that although some particles are going to be trapped at a low energy or higher energy state, the vast majority of particles at a given temperature will have an average amount of kinetic energy. And temperature is the measure of the average kinetic energy of all particles in a sample. So this is really important. This is a really interesting statement. So temperature we think of as how hot something feels, but scientifically really what temperature is telling us is the average kinetic energy of a collection of particles. So that makes sense then that as temperature rises, we're literally saying the average kinetic energy is rising, which means that things move faster and have like more speed and more velocity and might change state or something, because temperature is directly just telling us the average kinetic energy of all particles in a sample. So take a second here and look at this. So the connection here is an increase in temperature manifests as an increase in motion, which increases collisions, which is measured by increasing gas pressure. So as you increase temperature, molecules move faster, and gases like give off more pressure, and a solid might melt because it becomes the particles start moving too fast to stay arranged as a solid, and so on and so forth. So the main thing we're going to end up looking at when we're looking at phase changes in kinetic energy is temperature. in kinetic molecular theory because as temperature rises, our motion rises, and we have more kinetic energy. And as we cool down, we have the opposite. So as things cool down, they become slower, they get closer together, and yeah.